lecture will focus on functional analysis, which is really a broad term that describes a variety of different techniques that we can use to help us understand how a function is behaving at different x values in its domain. This lecture is the payoff for all of that work you did learning how to take derivatives. It's really the payoff for a lot of the algebra work that you did as well. So let's go ahead and get to it. What is it about calculus that makes Harris professors want you to learn it? In economics courses, basically it's that economists use it to find minima and maxima. Now, economists use it for lots of other things too, but for the sake of your Harris classes, that probably accounts for 85, dare I say 95% of the calculus you're going to need to do. So we're going to spend this entire lecture talking about how we find the highest and the lowest values of a particular function. Of course, calculus is useful for lots of other things, but in economics land, especially in introductory economics land, basically it's useful because we use it to find first and second derivatives in the process of finding the largest and smallest values of a function. So we're going to define extreme points a little bit formally. We can say that the function f of x has a maximum at some value of x that we'll call c if the function's value at that point is larger than the function's value at least over some little interval a to b. Now, I haven't said anything about that interval yet. The minimum of a function, the local minimum of a function, is, again, sort of same definition and in reverse, over some interval f of c is the smallest value. It does not matter how big the interval a to b is. We can make it arbitrarily small as long as there is some interval for which the above is true. We consider it a local minimum or a local maximum. So let's go ahead and just look at this crazy function here. And you'll notice that it goes up and then down and then up and then down and then slows way down, flattens out, and then keeps going up some more. It's also has two endpoints. Here I've marked them f and g. So if we want to talk about these different what are called critical points, the local maxima for this function are a, c, and f. Now I want to be careful about f. For the sake of this, I will say that the interval over which this function is defined is a closed interval. In other words, the endpoints are included. So the function is defined at that last endpoint. If this function were defined over an open interval, f would not be considered a local maximum. The same goes for point G. So here you see that I've labeled points G and B as local minima. G is a local minimum if this function is defined over a closed interval, so the endpoint is included. If it is not, then G would not be included in the local minimum. There is a global maximum, that is the highest point that the function takes on anywhere in its domain, and a global minimum, the lowest point that it takes on in its domain. Point E is what's called a saddle point. So anytime the function fully levels off but does not start to dip back down, it is considered a saddle point. In order to find critical points, there are really two different types of critical points you need to think about. The first is points at which the function's first derivative is 0. And the second is any point at which the function's first derivative is undefined. So that would include discontinuities of any type, endpoints of any type. It would include, like for an absolute value, the point where the function suddenly starts turning back around. It would include, for piecewise defined functions, possibly the point where there is a transition from one functional form to the other functional form, although there you would have to check the differentiability of the function in order to know that. We have a very, very useful theorem that explains why we care about critical points, and that is basically that all local extreme points, all local minima, all local maxima are critical points. The reverse does not hold. So there are critical points that are neither local minima nor local maxima. So to use the necessary sufficient language here, being a critical point is a necessary condition for being an extreme point. So now if we go back and look at the example that we just saw, the critical points A, B, C, D, and E are critical points because their derivative is equal to 0, while points F and G are critical points because they are undefined, because the derivative is undefined at the endpoints. So just like there are two types of critical points, there are two things you need to do if you're going to try to find all of the critical points for a function. The first is take the first derivative of the function, set it equal to 0, solve for all x values that make the function 0. All of those solutions are what we're calling critical values. And I want to attune you to this distinction in vocabulary. The critical value is the x value that makes the function, that makes the first derivative 0. However, it is possible to have a 0 first derivative, but to have the function itself be undefined at that point. So what you're going to do is you're going to find these critical values and then test whether f of x is actually defined at the critical value. If it is, then the point f of x is a critical point. So for the second type of critical point, you will find all values of x where the function is not differentiable. These are also critical values. And then if f of x is defined, then that the point on the function that matches up with that critical point, or with that critical value, is a critical point. Think, for example, about the distinction that I just made about the endpoints. So on that earlier graph, I said that these endpoints will be critical points only if this function is defined over a closed interval. So if it's an open interval, then the function is not defined at those endpoints, so the critical values are not critical points. So in other words, critical values are values of x. Critical points are points x f of x on the function, on the graph of the function. If you're looking for this second kind of critical point, basically you're going to be looking for any kind of discontinuity like endpoints, transition points for piecewise functions, or any kind of turning point like when an absolute value function suddenly reverses course at the x-axis, or any transition point on piecewise functions. Remember that for piecewise functions, there are some times if the function is continuous at the point and the first derivative is consistent on either side, there are times when you can have a differentiable point between two parts of a piecewise function, and that would not be a critical point if the derivative exists. All right, so let's go ahead and do an example. So here we have a function, x plus 1 over x. We're going to take its first derivative. The derivative of the first term is equal to 1. The derivative of the second term, so the second term is x raised to the negative 1. So its derivative, bring the negative 1 down and subtract 1 from the exponent. You get negative 1 over x squared. So you have 1 minus 1 over x squared. And for the sake of understanding a function like this, it's very, very important to try to get it into a fractional form where you have a common denominator. So you'll notice that I have taken x squared. I have multiplied, I've changed the 1 into an x squared over x squared so that I could have it over a common denominator. What that lets me do is that as I'm looking for a critical point, which from here on out I'll refer to as x star, I'm going to set this derivative equal to 0. what's nice about the way of writing it over a common denominator is that lets me factor the polynomial in the numerator. And once I've factored the polynomial in the numerator, I can ask myself, where is the numerator 0? The numerator is going to be 0 at any point, any point where the numerator is 0, the first derivative is also going to be 0. So once I've factored x squared minus 1 into x minus 1 times x plus 1, I know that for the first term, that implies a critical point at x equals 1. And for the second term, that implies a critical point at x equals negative 1. Also, so we've found the critical points where the derivative is equal to 0. Critical values where the derivative is equal to 0. We also need to find the critical values where the derivative does not exist. So here we're dividing by x squared. So that means that any point where the denominator is equal to 0 is going to be my derivative is going to be undefined. So that would just be where x is equal to 0. So I have critical values at negative 1, 0, and 1. But if I plug negative 1 into my original function, I get negative 1 plus negative 1 over negative 1 over 1, in other words, negative 2. So I get a critical point, negative 1, negative 2. If I plug 0 into my original function, I have 0 plus 1 over 0, which is undefined. So that critical value does not produce a critical point. And then if I plug 1 into my original function, I have 1 plus 1 over 1, which is 2. So I have the point 1, 2, which is a critical point. So those 3 critical values become 2 critical points. We can formalize this as the first derivative test for local extrema. You're first going to find all of the critical points. For each critical point, you're going to check the sign of the derivative on either side of the critical point. If you have a local maximum, the first derivative is going to be positive to the left, which is another way of saying the function is increasing to the left, and decreasing to the right. The derivative is going to be less than 0 on the right. If you have a local minimum, the first derivative is going to be negative to the left and positive to the right. And if you think just about what the graph looks like, to the left of a minimum, the function is decreasing. So the slope of the function is negative. And while to the right of a local minimum, the function is increasing. And so the derivative is positive. You have a saddle point if the first derivative has the same sign on both sides. When we're talking about checking the sign of the derivative on either side of the critical point, you can think about basically dividing the domain of the function into intervals split at each critical point. So let's look at an example of how that works. So here we have the function f of x equals x to the 4th plus 8x cubed plus 18x squared minus 8. So we're going to do the first derivative test. We'll take the first derivative, bring the 4 down, we have 4x cubed, bring the 3 down, 24x squared, bring the 2 down, 36x, and a constant's derivative is 0. To find the critical points, we're going to find the x values that make the derivative equal to 0. Notice that each of my terms has a 4x in it, so I have factored out the 4x, and I'm left with x squared plus 6x plus 9. Now, this is one reason that I tell you to, if you can see a common factor easily, to factor it out, because once I have it into this quadratic form, the term in parentheses is something that I can look at and I can factor fairly easily. So I go ahead and I factor the quadratic in the parentheses, and I notice that 3 times 3 is 9, 3 plus 3 is 6, and so I have 4x times quantity x plus 3 times quantity x plus 3 is equal to 0. So that produces 2 different critical values. From the 4x, we get that if x is equal to 0, the first derivative is 0. From each of the factored terms, we get that when x is equal to -3, the first derivative is also equal to 0. So now what we need to do is break the domain of the function, which in this case is the full real line, into intervals separated by each of these critical values. So I usually think of each interval separately, just consider them separately. I'm going to pick a value from each of the intervals. I will pick the value that's going to be easiest for me to do the calculations with. I cannot pick an endpoint. So I have to pick something that is on the open interval, so the endpoints don't work. So the easiest values for me to do calculations with, probably -4 for the first interval, -1 for the second interval, and 1 for the third interval. So what I'll do then is I'm going to plug this in, and notice that I'm going to plug it into the derivative, not into the function itself. So the value of the derivative at x equals -4 is 4 times -4 cubed plus 24 times -4 squared plus 36 times -4. You can do the math, it gets you -16. All I care about is the sign on the derivative for what it's worth. Sometimes that can lead you to speed things up. So for example, in this case, I had to actually calculate it out, but if I had only had an x cubed and an x term, both of those are going to be negative. So it's sometimes helpful to just check the signs on each of the terms in the derivative, and if they're all the same sign, you don't need to actually calculate it out. You can just say, yes, this is negative, or yes, this is positive. So now we look at the derivative where x equals -1. The value of the first term is -4. The value of the second term is +24. The value of the third term is -36. I add these values up, I get -16. For the third critical value, where x is equal to 1, that's one where I don't actually have to do the calculation. If I look at each of the terms in the derivative, each of them is positive. So I didn't need to calculate that this is equal to 64. I could have just said all three of these terms are positive, so my derivative is going to be positive. And it's really just the sign that is important. So now that I've done that, what I see is that the first derivative is negative on my interval -infinity to -3, negative on the interval -3 to 0, and positive on the interval 0 to +infinity. So what that means, as I'm thinking about each of my critical points, is that the only extreme point is x equals 0, because where x equals -3, the derivative has the same sign on both sides. So it's going to be a saddle point rather than a minimum or a maximum. I know that the x equals 0 is a local minimum because the function is decreasing to the left and increasing to the right. This is probably a good moment to take a little field trip into monotonic functions. So monotonic functions are functions that have the same sign on their derivative over a full interval. So I'm going to imagine a function f of x that exists on some interval and say that there are 2 points within that interval where the function is defined. We say that the function is monotonically increasing on that interval if the value of the function is at x2 is greater than the value of the function at x1 for all possible pairs of points where x2 is greater than x1. In some ways, the math here is a little, or the mathematical phrasing of this definition is more complicated than it needs to be. The concept is simply that no matter which pair of points you pick, the larger of the two values of x produces the larger value of the function. Monotonically decreasing is the same concept, except that big values of x2 produce little values of f of x2. Now, those definitions we saw from in algebra, we can restate them in calculus as follows. We can say that if the derivative of a function is greater than 0 for all values of x on the, a particular interval, then the function is monotonically increasing on that interval. If the value of the function is the value of the derivative of the function is negative for all values of x on the interval, then the function is monotonically decreasing on that interval. In order to test monotonicity of a function, you're going to find the first derivative of the function. You're going to find all of the critical points using that first derivative and also looking for points where the first derivative is undefined. And then you're going to take the domain of the function. This is just like what we just did with finding extrema. You're going to split it into intervals based on each critical point. And for each interval, including the ones where with the endpoints of negative and positive infinity, if that's part of the domain of the function, you're going to pick a test point. It has to be inside of the interval. It cannot be an endpoint. And between the critical points, you're going to test whether the first derivative is positive or negative. And then you can conclude, based off of that single test point, that the function is increasing or decreasing over the entire interval. Functions that are increasing on all intervals we call increasing functions. Functions that are decreasing on all intervals are called decreasing functions. So this is a good time to do this because the process that you use is very much related to the process that you use to find local extrema. So we'll go ahead and take an example. We have a function x squared minus 4x plus 5. We're going to take its first derivative. We bring the 2 down. The derivative of x squared is 2x. The derivative of 4x is 4. The derivative of 5 is a constant. We're going to solve this for for the value of x that makes it equal to 0. We find a critical value at x equals 2. The first derivative, as we look at that function, that's a linear function. There are no discontinuities. It is differentiable everywhere over the real line. So we can conclude that x equals 2 is the only critical point, which means that we need to consider the intervals negative infinity to 2 and 2 to positive infinity. The easiest thing to do for me is to set up a little table with columns for each of the intervals I'm interested in. I pick test points. Now, test points are really arbitrary. I just pick the values that I think are going to be the easiest to calculate. So I check for the interval negative infinity to 2. I check x equals 0. The test point A is equal to 0, so I get negative 4. And I can conclude that because that's less than 0, the function must be decreasing on the interval negative infinity to 2. I then plug in the test point A equals 3 to test the interval 2 to positive infinity. When I plug 3 in, I get 6 minus 2 is equal to 2. I get a positive value, and so I can conclude that on the interval 2 to positive infinity, the function is increasing. Now, what that means, if I have a function that was decreasing and then started increasing, I can conclude that where x equals 2, I must have a local minimum. So the value of the function at that point is 1, so 2, 1 is a critical point that is a local minimum. So let's do another example. All right, so here's a good example for you to try working on your own, pausing the video and then coming back. For this function, you should look for over what ranges the function is increasing or decreasing. You should find all of the critical values, all of the critical points, and all of the local minima and maxima. All right, so here we have f of x is 2x cubed plus 3x squared minus 12x minus 5. We're going to take the first derivative. We bring the 3 down, we get 6x squared plus bring the 2 down, 6x minus 12. The derivative of negative 5 is 0. I'm going to go ahead and factor out a 6. The reason that I do that is that it makes it much easier for me to just look at the function and understand how to factor it. So as I look at x squared plus x minus 2, I ask myself what values could I multiply together to get negative 2 when I multiply them but add them together and get positive 1? Well, positive 2 times negative 1 would give me negative 2 multiplied and positive 1 when added together. So I factor this out, I set it equal to 0, and so now I see that I have critical points at x equals positive 1 and at x equals negative 2. I set up a chart for myself looking at the intervals negative infinity to negative 2, negative 2 to 1, and 1 to positive infinity. I'm going to choose a test point equal to negative 3 for the first interval, 0 for the second interval, and 2 for the third interval. Remember, those test points are arbitrary. You can pick whatever you think is going to make your life easiest. So I plug in negative 3, and as I look at it, that very first term is going to be 9 times 6, so 54 negative. Minus 12 minus 18 is going to give me positive 24. So I can conclude that the function is increasing from negative infinity to negative 2. I plug in a equals 0. I get that the derivative is equal to negative 12. So I conclude that the function is decreasing between negative 2 and 1. I plug in 2 to the derivative, and this is I plug in 2, I get that the derivative is equal to positive 24, which is positive, obviously, and so I can conclude that the function itself is increasing over the interval 1 to infinity. Now, as I look at this, I can see that the function has transitioned from increasing to decreasing to increasing. So that lets me draw conclusions about what the function does at x equals negative 2 and at x equals 1. If I go from increasing to decreasing, that's a maximum. If I go from decreasing to increasing, that's a minimum. So I have that negative 2, and then the function at that point is 15, is a local maximum. And 1, negative 12 is a local minimum. The last point for this lecture will have to do with the existence of minima and maxima as we think about the endpoints for a function. So in this case, we have the endpoint where x is equal to 0 is part of the function. And so the function does have a minimum value at x equals 0. It does not have a defined maximum value. And the reason it does not is because that endpoint where x equals 1 produces a value of the function of 0.5. And immediately to the left of that, all of the values of the function running up to where x equals 1 are greater than 0.5. But the value for x equals 1 is defined to be part of the second region of the function, which is less than that. So here we have a defined minimum, but not a defined maximum. If we change the way this function is defined, just a very minute change, so that that endpoint is assigned to the left-hand interval rather than the right-hand interval, then that is a maximum point. And so now this function would have both a minimum and a maximum. Finally, if we looked at the function that did not include the endpoint 0, then we would have no minimum defined for the function, but we would have a defined maximum where x equals 1. Notice that for this function that's graphed, we have global minimum and maximum values that would be defined if the function were defined over a closed interval, but are not defined where the function is defined over an open interval. But the function does have local minima and maxima, which you can find by taking the first derivative. All of this is to help you think just a little bit about how you handle the critical points that arise from the problems with differentiability rather than the critical points that arise when the derivative is equal to 0.